Hello and welcome to Postgres FM, a weekly show about all things PostgreSQL. I am Michael, founder of PG Mustard, and today I am delighted to be joined by Jonathan Katz, a PostgreSQL core team member amongst other teams, principal product manager at AWS, and contributor to Pgvector. Welcome to the show, Jonathan.
Thank you, Michael. Happy to be here. Definitely a huge fan of your work, and I'm very excited for our conversation today.
Kind of you to say, me too. So, I reached out to you about this topic because it's about time we did an episode on Pgvector. How could we not have, given the last year? But neither of us knew it well. Both Nikolai and myself haven't used it until recently. Nikolai has been using it. So we wanted to make sure we covered it. And who better to, Andrew Kane was unavailable, and you are definitely the next best person. So we really appreciated all the content you've been putting out, the talks you've been given on this. So yeah. Thanks for joining.
Yeah, happy to be here. I mean, and by the way, when you say next best person, it's like well below Andrew Kane. Andrew has done phenomenal work on Pgvector over the past several years.
Yeah, right. And it has been, it's definitely predates the ChatGPT hype, right? It was a couple of years beforehand. Do you want to give us like a little bit of an introduction as to what it is and how you came to become involved with it?
Yeah, so Pgvector, at surface sounds, very simple. It's a Postgres extension that allows you to store and search vectors. And I mean, I'll talk a bit about how I got involved in it, but really to understand, how this all came to be, it actually helps to look back in history of Postgres. Postgres has actually always been able to support vectors, back since the Berkeley days. And it comes down to the array data type. So I mean, quite simply, a vector is, it's an array with certain properties. It has, a certain amount of dimensionality. There's certain things that each dimension must meet. And, there's all sorts of math around it. I mean, it's, there's about over a century of like what a vector is. But the reason why it was added to Postgres was not because of any mathematical properties. It was actually as a shortcut to be able to look up ACL rules. So instead of having to do a join to another catalog table to get the ACL rules, it's just embedded within a single column, as an array.
Oh, really?
So it's actually pretty cool. And then fast forward to the early 2000s, Postgres added the cube data type, which was allowed you to index up to 100-dimensional vectors, ultimately using a gist index. But it added all sorts of distance operations, which are the mathematical operations you need for a vector, which we can talk a little bit more about that as we get into this. But this is to say Postgres has actually supported vectors and vector lookups for a while, but certainly there's been a more pressing need for it. And, in terms of a little bit how I got involved, perhaps my, secret in the Postgres community was I originally wanted to go into machine learning when I was in college. And while I was studying it, I was like, oh, it's really fascinating, but to do anything with it, you're going to need a PhD and everything's ad hoc. And, I had a very entrepreneurial spirit. I think, I got impatient. And of course, I didn't have the foresight to see like, oh, this will be commoditized and it'll be very simple to access machine learning algorithms through simple APIs. So credit to where credit is due. Some very smart people, identified that and, I've been really building towards that. But again, working with machine learning systems in college, the fundamental data type was the vector. And back then, a high dimensional vector was something considered to be like 20 dimensions. And you think about it, Michael, like, what's a 20-dimensional vector? Like, I can barely, I can understand 3, 3 is like points in space. I can understand 4, points in space moving around. What's 5?
4 plus time, right? Yeah.
Yeah.
I studied, I don't know if you know, but I studied maths at university and did pretty much just pure. I did a tiny bit of stats and a tiny bit of mechanics, but I was best at the pure stuff. And yeah, 5 dimensions hurts my head to think about it, like or to try and conceptualize it in any way.
Yeah. It's funny that you say that. I studied math too, though. Like, I would say I was much stronger on the computer science side, but real analysis was one of my favorite classes because, you were proving like everything in n-dimensional space. And again, like everything's a vector or a matrix, you basically spend a semester just studying vector spaces and all their properties. And to me, like, that was fun. And maybe it was telling, fast forwarding, 20 years later. But, my journey back to vectors came probably a little bit later than, some folks. The Pgvector project started in 2021. Andrew had the foresight to see that a lot of data could be generated around, machine learning and AI systems. And Postgres didn't really have support for the types of vector lookups that we needed. So let's back up a second. So I said that Postgres had support for vectors all along, but it did and it didn't. one thing about relational databases, and Postgres in particular, is that you look for exact results. You say like, hey, I want to find like the 10, let's say I want to look up like Michael or Jonathan in a database. I'm going to write a select query with a where Michael is, or where name equals Michael, right? And you expect to get the results for like Michael, like all the Michaels in the database. Same thing when you're looking up points. Postgres has the ability to index things by k nearest neighbor, or find all the points that are around me. And again, if I say like, hey, go in and find like the 10 closest coffee shops to me, you're going to find exactly the 10 closest coffee shops. And these things work in, like 3 dimensions, 4 dimensions, which is typically where Postgres operates. If you take the PostGIS extension, which adds geospatial support to Postgres, you can index 3 and 4 dimensional points, and you can do it quite well. The GIST and the SPGIST indexes provide the ability to write these indexes. But as you start adding dimensions, you go from, even like 8 to 10 to 100, like, which is the limit of the cube extension. It's going to start getting very exhaustive. First, in terms of placing the vector or it's not really a point anymore, but think about it as a point. You're trying to place this in space and try to figure out, I have 100 dimensions and I have to like situate, somewhere in my graph where that is. It's going to be, very exhaustive. And then even if you are doing some kind of exact nearest neighbor search or some index search, there's going to be a lot of cost to it.
Yeah.
And this is where Postgres, started falling over in a ways, because a lot of these vectors we're seeing, if you look at some of the popular embedding systems, they're 1,536 dimensions, which again, mind-blowing number. Like I still don't even know what like a 5-dimensional vector is. And here we're talking about 1,500 dimensional vectors. And to do an exact nearest neighbor search, as they call it, or the key nearest neighbor, you have to compare against every single vector that you store in a database. So you have 1 million vectors that are 1,500 dimensions. You're doing 1 million times 1,500 computations on them. And that's really expensive. I can tell you it's very expensive because I've had to, I've been personally, benchmarking this for quite a bit.
And it makes sense, right? It's at minimum a sequential scan of the entire table plus all of the CPU of doing those calculations 100 times per, 1,500 times per row.
1,500 times, yeah. And we can talk about in terms of like all the, all sorts of the optimizations that are in place there.
Yeah.
But this is where like that exact nearest neighbor problem gets hard. And again, Postgres didn't have the indexing mechanisms to handle it. Probably we'll further dive into that as we talk more. But I'll say one of the big ones is just in terms of just storing the data. It's storing the data within the index, that you have to fit your index value, for a single row within an 8 kilobyte limit within the page. So that's already going to start creating some constraints. Now, what's also happened over the past 20 years, since the cube type was added in Postgres, was a whole field of modern vector research, as I like to call it, and start getting to this idea of approximate nearest neighbor. And the idea with approximate nearest neighbor is that you're trying to find your nearest neighbors, but with a best fit, which is you're not going to search every single vector in a particular table or database. You're going to search a subset of it, and you're hoping that you're seeing the representative set of the data you want to return. Now, again, for us relational database folks, that's mind-blowing. It's like, wait a second, I'm not returning the exact answers. I'm returning like an approximate subset. And I'll tell you, the first time I used Pgvector and I was playing around with it and I was not getting like the results I expected. At first, I'm like, oh, this is broken. This doesn't work. This doesn't make sense. And, that was the app developer in me, the DBA in me, that started diving deeper and trying to understand like, oh, wow, there's like a whole science around this that we kind of have to relearn when using a database.
Yeah, well, I often say to people, you can run a database without adding any indexes, and you can run any query you want and get the results back. It's just faster to use an index, where your query result will not change as a result of you having an index. And that sentence is no longer true if we include these approximate nearest neighbor type indexes. Yeah. So I have to stop saying that or work out a way of caveating it.
Yeah. Well, just say, in this world, when you're dealing with, vector similarity search. But back to the question, how did I get involved in Pgvector? So rewind to about the end of 2022. We may have heard about some of these generative AI systems that were capturing the imagination. And we go and we, type things into them and we get back these, human-like responses. And suddenly it's like, we're trying to think like, oh, what are all the different ways to use it? And one of the techniques that emerged, as these systems grew in rapid popularity was retrieval augmented generation, where these large language models, foundational models, have trained on vast quantities of data, typically publicly available data. But you may have data sitting in your database or there's some other private source that is not publicly available for good reason. It might be your product catalog or information related to a documentation collection that you have. But you're trying to deliver something to your users, your customers, that can take advantage of what's in these generative AI systems, but provide that personalized experience. And to do that, you need some way to be able to take that data that exists in your private databases and safely and securely augment them with your foundational models to be able to deliver that. And that's where the vector search comes in, because the vector search provides a representation that you can search over and be able to augment those answers. So seeing this is how people want to use it, and frankly, people want to use it with Postgres. A lot of the user and customer conversations I had were around, hey, I already have this data existing in my Postgres database, or I've already built all my search mechanisms around Postgres. I want to be able to simply use it. And there was an extension that did this, and it was Pgvector. So for me personally, it started to become a perfect storm. I'd studied this vector stuff in college.
Yep.
I was a hobbyist machine learningist, albeit the field has gotten way more complex than when I studied it. And I happen to like databases as it happens, particularly Postgres. So I looked at this extension. It seemed like a lot of people were starting to adopt it in rapid fashion. I mean, if you look at the star history of Pgvector, it's a curve like this. I've never seen that before for a Postgres extension. But I stepped back a minute as well, and I saw that these are net new database workloads. A lot of what we see in Postgres in the past has been moving database workloads over, a lot of traditional, transactional relational applications. Though, I call it you might call it once in a generation, which in the tech world is every 10 years. There's this new workload that emerges that just generates net new data. So about, 10, 15 years ago, we saw that with JSON. We developed this lingua franca across the web that made it simple to communicate between all these APIs, but there became a demand to be able to store JSON data directly in a database and easily query it out. And Postgres developed a solution for that, being the JSON and the JSON-B data type, which became quite efficient at being able to query it. And what was nice is that the Postgres community rallied around what people were doing and created a very efficient, effective solution. Side note, I've talked to one Postgres user that has 40 terabytes of JSON in a single database, and they say Postgres rocks it. Which I'm like, wow, that's great. I'm glad it works.
That's so nice for you.
yeah. I'm like, it is really cool. Again, I can't figure out how I would personally do it, but I'm glad that it works really well for them. But we're seeing something similar with vectors. Vectors are just a data type. It's actually a well-studied data type. It's something you kind of look at, in your introductory computer science classes. But when it comes to efficient data search and retrieval, there's so many nasty properties with them that make it a really fun and challenging problem to work on. But the thing is, this is this new workload that is going to be available to databases, including Postgres. And for me personally, I want to make sure that we're positioning Postgres in a way to handle it. So where I got started with Pgvector was first using it, helping to get it deployed at AWS. But like any open source project, if you're interested in it, just participate. There's a few things that I particularly focused on, which was performance, both from a contribution standpoint and a testing standpoint. And first, I would just want to say a large chunk of the performance features have been developed by Andrew Keen. He's done an awesome job on it. And more recently, Heikki Linnakangas has even further improved the performance on it. Nice. Where I stepped in was both just benchmarking to make sure that we're focusing on the right areas of performance and trying to prioritize what things to look at. And a few patches here and there, particularly around some of the index costing early on for IVF flat. But
yeah, I saw that.
Oh, thank you.
I would love to get onto performance and tips for people. But before that, I hadn't thought of this as net new data. That's a super interesting way of looking at it. And I hadn't thought of JSON as necessarily net new data. I was thinking of it much more along the lines of the NoSQL workloads that felt quite competitive with the relational for a while. But yeah, really interesting way of looking at it. And it does feel like an opportunity, much like that did, to be able to handle more within Postgres with all of the benefits that we've done episodes on the pros and cons of having data inside and outside using specialized databases, but you gain so many benefits, like the transactional nature of things, or the low latency, or being able to join things together. Like, there are so many benefits of having it all together. So, and not to mention the lower maintenance overhead or the lower operational knowledge needed of managing multiple systems. So yeah, great point. Love it. Thank you.
Cool.
Yeah. So I was looking at through your PRs, and the IVF flat and the IVF flat costings looked like a core improvement to make sure Postgres is using indexes in more cases where indexes would be faster, which is the age-old cost optimization problem. And also more recently, you did some great blog posts on the addition. So IVF flat was the first index type that Pgvector supported. And then more recently got added not as new as I expected when I looked back at the history, but the competing index type, HNSW, which you've also been involved in tuning, I've seen.
Yeah, so IVF flat was first. And I think, one of the reasons why is that it is a bit simpler to implement. So it's a clustering algorithm. Clustering algorithms are well studied. I mean, there's continually being improved. But one of the things you have to think about when you're looking at implementing these algorithms is that something that might work for an in-memory workload doesn't necessarily work for a database workload, where you're going between memory and an I/O level, be it wherever your storage may reside. And with IVF flat, where I began getting involved was at AWS. We had rolled out Pgvector. I started talking to some of our customers who are early Pgvector adopters, and it was definitely all over the board. But I was talking to one who's definitely very savvy on vector searches in general, and they were remarking that when they were trying to increase the number of probes in their query, so let's step back. So the way IVF flat works is that you build clusters of vectors. So let's say let's keep it simple. You have like 10,000 vectors. What you want to do is you want to try to bucket them into lists. So let's say you want to have 100 lists. So there would be 1,000 vectors. No, there would be 100 vectors per list. There we go. Clearly, I did well with my math major.
Arithmetic was not included, right?
Yeah, exactly. After a certain year, you never saw a number. So you have 100. So let's back up. So we have 10,000 vectors. We want to put them in 100 lists. Each have 100 vectors. What happens with IVF flat is that you try to find centers. So you want to find all the vectors near a particular center, because the idea of that is that those are going to be the most similar vectors to each other. So that way, when you do a lookup, you're going to one of those centers. And the idea is that these are likely, by approximation, the vectors that are most similar to the ones that you're looking up. However, it may not be, because let's say you have, 2 centers here, and your query vector is here. Yeah, which one are you closer to?
I had to have somebody explain this to me like twice. And the second time they used the analogy, it worked better for me. If we go back to 2 dimensions and look at, let's say, a map of, let's say, Europe, and we had the countries laid out, we could have, for example, it's probably not a great analogy, but you could have the capital cities. And first off, we could compare any one point and say, which capital city is this nearest to? That's a much cheaper operation than looking at every single city. And then we can go into that country and look at which of the actual towns or cities are we closest to. But if something's close to a border, or the fact that not all countries are the same size, you can end up in situations where you don't necessarily get the right center or country by doing that first one. Is that a reasonable analogy?
Yeah, that's really good, because I started thinking about that. So I'm based in New York, and I'm thinking, what capital am I closest to? It's technically Trenton, which is in New Jersey. So
there you go.
And if I just looked at one probe, it would say like, oh, you're in New Jersey. Yeah, actually, I think it would probably take 3 probes, because I think Albany is the 3rd closest capital to.
There you go.
So there you go. Yeah, great analogy.
So probes is the so you'd then do that first search and say, which are the 3 closest centers?
Yeah, centers, list. List is the term that's used. You might also it might be used interchangeably with centers.
So if we increase that number of probes, we're increasing the cost of doing the query, because we're looking at more things, we're comparing to more things, but we're increasing the likelihood we're going to get back the correct result, or the number of things that are correct, or
right. In our expected set. So the measurement of expectation is recall. So if you know that these set of vectors are like your actual 10 exact vectors, but you get like 8 out of the 10, then you have 80% recall. So with IVA flat, as you say, as you increase the number of probes, you're going to increase your recall. But you are going to increase the query time.
Yeah.
Now, in that patch you were talking about, the problem was that we were actually overcosting. So anytime we were above 5 probes, we then flip back to a sequential scan, which will give you 100% recall, but like it was taking the query time from, it was like a 50x increase in query time based upon the data set. And we definitely still had room to grow. So the first patch really was focused on let's get the costing to be a more reasonable level, which gets into startup costs being one of those elements. For me personally, it really was my first time like diving into the query planner code, and definitely saw like all sorts of interesting things. I mean, first off, like the query planner code is there's a level of brilliance to it. Like it encapsulates a lot, and like the work that folks have done over the past 35 years tuning it is quite remarkable. I'd also say that it is quite clean. Yeah. It takes a lot, like there's a lot of it, right? So like there's a lot to dive into, but like once you get into it, you can navigate your way around. Editing it is another story. It's one thing to understand it. It's another thing to post a recommendation. But what's really cool about Postgres is that you can make a lot of impact within an extension. Or basically, you can add this functionality without having to fork Postgres. You could just write it in a separate module and then add it in. And Pgvector does this through the index access method interface, which is actually quite robust. Like we build index types that don't fit the natural B-tree ordering of a relational database. So it's quite powerful there. And we were able to ultimately get, I'd say, pretty good costing for IVA flat without having to make any upstream modifications to Postgres.
Nice.
For now.
And the other, so on the IVA flat, because of these centers, my understanding is it doesn't necessarily, it suits a data set you already have that is static or not changing much, because if you're adding data, it can't adjust as it goes. So there is this trade-off inherent in it. And I'm guessing some of the customers you were talking to had different workloads that wouldn't necessarily suit that. And what happened with your customer conversations next?
Yeah, so that's a good discussion, and I'd say let's burn it. Like it's users of Pgvector in general. A lot of these conversations I have in the open source project, which is again awesome. So that's definitely something that came up. That if my data set, if I keep adding vectors to the data set, or every now and then you update them as well, or even delete them, what happens is that the centers start to skew, because where you calculated where all these centers are may start shifting. So your results might start shifting as well, and you might not be getting the expected results or the recall that you'd want to see. The other thing as well is that for a lot of app developers, I mean, first off, again, you have to wrap your head around approximate nearest neighbor, that you may not be getting the exact results that you expect. And like I said, I tripped up over that as well. Like it's normal to make that mistake. You have to learn something different. The other thing is that it started turning app developers into DBAs, in the sense that you had to worry about some of your tuning parameters. And granted, there's two of them, right? There's the number of lists when you build the index, which is not necessarily terrible, because you are, as an app developer, you're still writing your SQL code, you are creating that index. But you have to think, like, what is the number of lists? And the Pgvector project gives some guidance on the number of lists to pick, but it's still like you have to experiment. And then you have to be mindful of things like, oh, am I adding more data to it? Do I need to reindex? How do I reindex? Who's doing the reindexing, etc. And then you have to select probes, which again, you're writing queries possibly in your ORM, and suddenly you have to set like this magic parameter to choose, how many of these lists you want to visit during a query. So it's not as simple as set and forget. And, that's when I come back to my history of being an app developer, I always want to just write code and I want to all just work. I happen to explore the database as a side effect of that, not, as a first order principle of that. So it became time to explore an algorithm that could be closer to set and forget. Like none of these approximate nearest neighbor algorithms are set and forget, but we can at least make it easier. And this is where HNSW came in, hierarchical navigable small worlds. So HNSW is a little bit different than IVA5 because it's not cluster-based, it's graph-based. And when you hear a graph, you can actually almost hear, a graph is a superset of a tree. So even though Postgres is very tree-based in a lot of its algorithms, you can implement something graph-based as well, particularly with the custom index framework. And the way an HNSW works is that you build a hierarchy or layers of vectors. And as you go down the hierarchy, the layers get denser, denser, and denser. And the idea is that you start at a top layer and you try to find, which vector am I closest to? You find like your local maximum, or effectively like the vector I'm closest to. Then you go down and you search within that area, and you find the one that you're next closest to, and you go down, and then it's even denser, and you search, and so on and so forth till you get to the final layer. And the vectors that you should be clustered around are most likely the vectors you're most similar to. When you're building the index, there's two parameters that you have two index building parameters. You have something called M, which is the number of vectors that you're linked to in a given time. And Pgvector defaults to 16. And you have something called EF construction, which is the search radius that you're keeping as you're descending down it. The idea that if you look at a larger search radius, you're going to see the vectors that you're more similar to. The idea also with a larger M is that you're going to be clustered to vectors you're more similar to as well. But there's definitely trade-offs between how you pick that. What happens is that when you actually do the query, you should be looking over a smaller space. So IVA flat is going to grow linearly as you add the number of probes, and it's going to grow linearly by the number of vectors that are in each list. So the idea is that if you can keep the list relatively small, you're going to be able to do faster searches with IVA flat. But there's also trade-offs to that as well, that you might not be getting the recall that you want. So you can see on IVA flat query can get expensive over time, particularly if you're linearly growing it. With HNSW, you're only searching over a smaller subset of the space. And again, this could be dictated by your one search parameter, which is EF search, but you're only looking at a subset of the graph. So you're going to be looking at far fewer vectors. And the idea is that you're being put into a cluster that's very similar to you. So there's trade-offs. With IVA flat, I can build the index super quickly. And technically, if I'm only using one probe, I might be able to query it super quickly. But the trade-off is that to boost recall in IVA flat, what we've seen empirically is that it's going to start getting more expensive. With HNSW, we can query really quickly, and we can query, and again, the results are showing that we can query and get high recall, or we're basically seeing the expected results, and with pretty good accuracy. But the trade-off is going to be on the build time, because we're going to have to do a lot more work up front to build that hierarchy and see all of the, basically try to visit enough vectors that seem most similar to me. And that's the push and pull between the, these two algorithms, and just, vector similarity search in general, is that you're going to have to pay the cost somewhere, and you have to figure out what that cost is going to be and what makes the most sense for your workload. Yeah. With HNSW, at least, if you're willing to pay that upfront cost, which, it seems like a lot of folks are, you are going to get like this very high performance, high recall system, most likely. And again, there are other factors that go into this as well, including your embedding model, or how you're querying the data, or how quickly you're ingesting the data. So like, there's a lot to consider here.
Yeah, I'm a performance guy at heart, and I love it when there is actually a true trade-off, and people in different situations will have different preferences. But to me, it seems like a lot of the currently popular use cases can pay, or have a desire for as high a recall as is possible within a latency threshold. Like, so they're willing to pay some latency and build, like, index build time costs for as high a recall as possible to a point. And then that everyone has like a different point at which that is. But yeah, I actually wanted to ask almost the opposite question. Do you see some use cases where the index build time itself is the primary driver, or any other reasons that you're seeing people choose IVF flat at the moment?
Yeah, there are cases where you might be needing to do rapid loads and a bit of analysis, but it's very transient. Where I want to do so one of the cases I've heard is that there's a system with, let's say, like 100 million vectors, and it's really more about getting a rapid build and doing a spot check on the data within it, as opposed to having something that's permanent that needs to be run all the time. I think it's like a lot of these transient or ephemeral workloads where an IVA flat index can make sense. But frankly, like, I've talked to people who have just rolled out production systems with IVA flat with several million vectors in it. They're perfectly happy. They're like, we're getting the results that we need. We're getting it in the amount of time that we expect it to return the query in. And they're completely fine with it. So some of it is personal preference. And some of it, like I said, depends on other factors, such as the data that has been vectorized. Like, how similar are the vectors based upon the embedding model? And are you able to get the distances within a range where you're seeing that the set that you want?
Awesome. That's really interesting. So you've got a great talk on this that I'll link up that you gave recently at PGConf EU. And you've also had a couple of great blog posts on the releases around 0.5.0 and 0.5.1. I'll link those up so people can read them in their own time. I did actually want to ask you, you mentioned some tuning, like some people becoming DBAs and having to think about, you mentioned right up top the page size of Postgres, for example. Do you want to talk a little bit about why that's important and some of the lower level stuff that people need to think about when they're doing this?
All right. So tuning or technical, I heard two different things.
Let's go tuning as more practical. We don't have to explain toast. We've done a whole episode on toast before, but there was some interesting stuff in there that really got me thinking that I hadn't thought about before.
Yeah. There's a whole bunch of areas to go into. So just to briefly recap, because I think this does impact tuning. So toast is a system that, step back further. So the foundational unit of Postgres is the page. Mm-hmm. That's the atomic unit. When you store data, you're actually storing it within this atomic unit. You're not just storing, a row randomly on disk. It's going to be, fit within a page. By default, the page for Postgres is 8 kilobytes. Now, you can recompile Postgres to use a different page size, but most folks just use the default, and for a lot of good reasons. What's interesting is that, so if you have data that doesn't fit within a page, what happens is that it gets toasted. And it gets stored out of line, and you can store it arbitrarily large. I believe it's up to 1 gigabyte per field. Now, what's interesting, there's a few interesting things here. So first, Postgres has what's called a minimum toast threshold, which is 2 kilobytes. So anything above 2 kilobytes is going to get toasted, unless you change that threshold. The second thing is that index pages must abide by that 8 kilobyte limit. And you can actually toast data in line with an index page to shrink it down a bit so you can get a little bit more on that index page. But if it's going to be over 8 kilobytes, Postgres can't index it. So this is where it gets interesting for vectors for a few reasons. So first, any vector that's above that 2 kilobyte threshold, which I believe, I forget off the top of my head, it's around like 514 dimensions for Pgvector currently, is going to get toasted. Okay, that might seem okay. But any vector currently, there's a hard cap in terms of indexing Pgvector vectors of 2,000 dimensions, which there are some valid use cases I've heard of vectors that go beyond that size. But typically, most things are going to fall within that range, for now. Now, there's a few things here. Like first, you're like, well, you say you can toast things in line. So why can't we toast these vectors in line? Well, I hate to be the bearer of bad news, but it's actually very challenging to compress effectively, 2,000 dimensions of, random, floating point numbers.
Yeah.
So there's not really much you can do other than dimensionality reduction to shrink it down. There's some techniques that are out there called quantization, which you can touch on after this, but, they all have their trade-offs, such as, losing information. So the second thing is that toasting can screw up the query planner a bit. What do I mean by this? So currently, when the query planner is trying to estimate parallel workers, or essentially reading data in parallel, it's going to it basically looks at your heap pages or your main table pages and uses that to drive the estimate. And the thing about toast is that your heap pages actually be quite small. In this case, let's say if an ID in a vector, well, I'm not going to have that many pages in my regular heap because it's just going to be a bunch of IDs and a pointer to my toast table. The toast table is going to be quite large, and likely you need those parallel workers to suck all the data out. But what Postgres is going to do is it's going to underestimate the workers today. And it actually makes sense historically because the data that you typically toasted was not in your search path or your ordering path. It's typically something that you need to do some post filtering on as you pull it out. Think like, a big blob of text.
Yeah.
But here we are actively querying the vectors. We are calculating distances between them. So we probably want them closer to like our main set of data. Now, we can choose to store the vectors in line. You use this technique called set storage plain, and that will keep your 1500 dimensional vector in line with your, with your other table data. But also keep in mind, this is going to cost a full page because a 1500 dimensional vector is about 6 kilobytes, and Postgres is just going to have to allocate a page for each of them. So, no matter what, you're storing 8 kilobytes of data in them. So this gets very interesting. Yeah. So in terms of tuning, again, part of this, you got to look at what your workload is and what makes the most sense. In that, what we're seeing so far with at least with HNSW is that, even if you're toasting a 1500 dimensional vector, the estimates are still pretty good overall for making sure that you're using your HNSW index. I haven't seen as much impact there. We saw more impact, particularly with IVF flat, based upon some of that costing model.
Interesting.
But I think this is one of those areas where I think there's some improvements to how we work with toasted data upstream. I think I have a couple of emails or threads, on that subject. And if I get my C chops better, maybe I can propose a patch. But cool. That's like one area to be mindful of is like how you store the data. And again, I think we're starting to get a little bit more set and forget there. But I think as we see like these workloads increase, it is definitely something to be mindful of.
From a bias standpoint, some Postgres supporter and advocate, I've seen quite a lot of benchmarks that show Pgvector doing very well as a vector database compared to other dedicated systems. So that's impressive considering they're probably not even tuning some of those lower level things while doing those benchmarks. So it's exciting for me to hear that there's actually some potential further wins there on the Postgres side.
Yeah, I mean, and maybe like hot off the presses, Andrew proposed a patch last night for speeding up HNSW index building. Since like the 051 release, there's already been a lot of work to improve this, but the patch last night like even further accelerates it. So there's support for parallel builds for HNSW indexes. And the initial work still had to leverage a lot of the data coming from disk as opposed to being fully in memory. The proposal last night is fully in memory. And I actually did a test. I was so excited to see it. I did a test. I have this 10 million, 1500 dimensional vector data set, or really like 1536 dimensional data set.
Yeah.
Random vectors, right? This is really more just for like beating up on performance. I'm not measuring recall here, which for real benchmarks, you got to measure performance and recall. But I'm trying to just understand like how quick is the index build time. So I did this with what's currently on the master branch to date. I used this, and then I also did the test with the HNSW fast build branch, which is this in-memory system. So I saw a couple of things. So first, this new branch was about, I think it's 7.3x faster at building HNSW index than the other branch. And just to compare, like, let's give some real numbers. So the old branch, which is, the unreleased support for the HNSW parallel builds, it took about 3 hours and change to build the entire index. And this was with like 64 parallel workers. I'm throwing, this is a big beefy box.
Yeah.
With the new branch, it took 25 minutes. It's a huge, like that's mind blowing, right? These are big vectors. You're doing a lot of computations. And I even had cranked up the EF construction value, which does increase the time. I did compare it to this previous method I've been recommending, which was concurrent inserts. And I just, I did a spot check between a blog post I wrote about it and this new patch. So in the blog post where I had a lower value of EF construction, it was, I think, 64. I was getting about a little bit over 1,000 vectors per second, looking over the entire front. With this new technique that Andrew posted, I was getting over 6,500 vectors per second.
Yeah.
So again,
similar
huge,
there as well. Yeah.
So, and this is what's cool about this, because this is one of those set and forget things that you might need to tweak. You might need to tweak like one parameter. In this case, I tweaked max parallel maintenance workers. But again, huge performance boost in terms of the index build, and it simplifies it too, because now it makes it truly viable to say preload all your vectors, which will be a much faster operation than doing a concurrent insert. I mean, you could still use a concurrent insert and even like further speed up your load of your vectors. But then you can just do create index, embeddings using HNSW, and boom, like you have an index way faster in other systems. And like this is a key thing too to look at. You touch on this, Michael, is that when you're dealing with this vector data, you got to look at everything. You got to look at your ingestion time, your index build time, your query time. And you have to focus on all these things because there is a trade-off with all of them.
Yeah. Well, exciting times ahead. It feels like the most rapidly improving area at the moment, and for good reason. So I saw it's got a great changelog, Pgvector, and I saw there's like even the unreleased part. So 0.5.2 is currently on there and unreleased. Is there anything you're particularly excited about that's coming up, or anything not on that list that you'd love to see?
Yeah. And I think this is where it really helps to have feedback on how people are using it. So obviously very excited about parallel HNSW builds. Like this is, even like in the middle of that test I was running last night, like I emailed Andrew, like, Andrew, the results are amazing. Like I can't wait for it to finish. Like I can see where this is trending. So there's two things in particular I'm very excited for. The first, and we'll see if it makes it in, but it's around pre-filtering. So a lot of the queries today we've been seeing is like select star from vector table, order by, blah, 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 limit 10. Find me my 10 nearest neighbors. But what's happening in practice? In practice, it's like select star from table where it has some condition. Category ID equals this. Order by, blah, 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 blah. So what this is kind of like is really a multi-column index, because what'll happen is like today, either you won't use the index, and effectively you're doing an exact nearest neighbor search, which means very accurate results. And maybe, your data set gets sorted down to a small enough value where it doesn't matter. Like you're getting a very fast search. But what if you have multiple fields that you need to filter over? Or what if the data set you get back is 50,000 of these, 1,500 dimensional vectors? Like that, this can be exhaustive. So there's a patch out there. It's based on a newer paper called HQANN. You check in the Pgvector repo right now.
Yes.
That lets you build effectively a multi-column index where it's able to build the links or group together. Well, there's two things, right? Because you still want to be able to search over your entire vector set and find your most similar vectors. But you can also group, it also groups the vectors by your filters, so that way you're searching over just your filters, and it does that pre-filtering. This has come up by, it's almost like this is like a what have you done for me lately feature, because as soon as you put it out, users find more of these case studies emerge, and users find hey, I really need this. But what's great is that there are people who are testing it against real data, and this is where, if you want to be involved in Pgvector, you can help. Is that you see these patches out there, please test and report back on them, because if you're finding the HQANN branch useful, describe your use case. There's an open issue where people talk about, they might say hey, I really need this. And what makes it super valuable is when you talk about here's exactly how I'm using it, because it just further justifies this is the right direction. I mean, one of the big goals of Pgvector is to try to keep the code base simple to maintain and also make the product simple, or the extension simple to use. So hearing more about what people are doing is great. Another patch that I'm excited for, and again, we'll see if it makes it into 0.5.2, no guarantees, is being able to support smaller dimensional sizes. So right now, dimensions are 4-byte floats. But there are definitely embedding models that provide 2-byte floats or 1-byte unsigned integers. So there's a couple of branches that have those in there. But again, hearing those use cases will help further support it. Because the added bonus to supporting these smaller dimensions is that we can index larger vectors, and that'll be able to go beyond that 2K limit.
Yes, interesting. The one final question I had is, do you see any world where this becomes part of core PostgreSQL in the long term?
Yeah, so at PGCon 2023 last year, I had a lightning talk, which is basically to first shout to the wind to the community, hey, these vector workloads, this is real. That was still early, but it's hey, this is coming. There's I call it a storm of data coming. We want to make sure Postgres is positioned for it. This is very similar to what we saw with JSON. And I was able to get an unconference session as well where we discussed it. Nice. And the general consensus was, in the fullness of time, it does make sense to have something like this in upstream Postgres.
Great.
But I think there's a few things here. First, we have to look at release cycles. Postgres releases once a year. In fact, the feature freeze for Postgres 17 is coming up in about less than 3 months. But effectively, there's if you think, let's say come up with the idea we want to support a vector data type right now, or let's say after feature freeze. I mean, there's effectively 18-month window before it gets in, because we have to go through the whole cycle. And given the pace that this field is moving, we don't necessarily want to wait on the Postgres release cycle. So being able to do this work in Pgvector or other extensions does help accelerate adoption of Postgres as a vector database, so to speak. The other thing is that once it is in upstream Postgres, that is the on-disk format. That is the rule. Yeah. And Tom Lee made a very good point during that unconference session, which is let's see how things shake out in terms of what the on-disk format is. Now, Pgvector is also trying to stay true to that contract and try to keep the on-disk format as effectively not to change it, because as soon as you change it, you got to rebuild, reindex, restore everything. That's a costly operation. So Pgvector is trying to apply the same level of rigor as Postgres to implementing these features, but it can move a little bit faster because it is an extension. It can have its own release lifecycle. So I think that's where is that I'm not going to say this is an official or unofficial community position, but is there interest in supporting it upstream? Absolutely. But given the rapid emergence and development we need to make, we're trying to make as much progress as possible within Pgvector. Here's the other thing too, like the big difference between now and JSON. We have the index access method. We can do this in an extension. That is a big change since 10, 15 years ago.
That's really interesting and good to know. There's another big difference, which is cloud providers. So whilst it could be in core Postgres, currently a lot of people that install Postgres themselves or manage Postgres themselves more specifically can install Pgvector, and people that don't are often on a managed service provider. Those folks, most managed service providers have added support for Pgvector already, which is the fastest I've ever seen them add a new extension. And it's been pretty much everyone. So most folks that want access to Pgvector, at least some version of it, maybe not always the latest version, can have it now as well.
Yeah, it's definitely exciting to see all the adoption of Pgvector. And to tease a little bit, I still think the best is yet to come. Like, I think Pgvector has made a lot of progress in the past year. I mean, it's been a tremendous work by the community, and in particular Andrew. Like, I can't say enough nice things about the work Andrew has done and really the diligence he's put into it. And I still think there's more to do. Like I said, even just the patch that came out last night, just shows that there's still even more performance that we can get out of it.
And for folks listening, that we're recording on the 16th, so I'll link that up. Wonderful. Jonathan, thank you so much. Is there anything else I should have asked you but didn't, or any last things you wanted to say?
Yeah, I think one of the big things, when we think about contributing to open source is, writing a patch, writing code. And I'm going to say this in the context of Pgvector, but I think this applies to any project. I mean, even Postgres itself, is that there are many different ways to contribute. Testing is huge, because testing, particularly if you can test something that's close to a real workload, like don't test your production workloads with these things, but like test something that's close to production. That helps, because that helps drive the use case, and hearing how you use something and just talking about your different use cases and being supportive of the community in that way, that helps. Helping to write documentation, helping to advocate for something that you think can help others. Again, all these things can help a project. So if you want to contribute to Pgvector or Postgres, there are a variety of different ways. And maybe to as it's top of mind right now, PGCon, which was effectively the annual developer conference, it's evolved. It's now called pgconf.dev, pgconf.dev. It's being held in Vancouver at the end of May. I can tell you, I can almost guarantee vector workloads will be a topic of discussion there. But just all things Postgres, and the idea is that while certainly a lot of the folks at the discussions are around technical hacking topics, really, if you step back, the gist is how do we continue building and growing the Postgres community? So if you the CFP actually just closed yesterday, or when this airs, probably a few days before, but that's a great way to participate as well, even if you're newer to the community, because I know personally at one point I was new to the community, and the first time I went to PGCon, I'm like, oh my God, like I know nothing about how a database works. Like I can write a select query, but geez, but it is a way to help have impact on the community. And, just talking to folks who are working on the software, or working on events, or hosting podcasts, or finding ways to help grow the community. It's a great way to participate and help grow. So certainly, think about attending and participating. And again, there's all sorts of different ways to contribute. So that's the parting message I have. I'm far from a database hacker. I can write like a couple of lines to see here and there, but where I've found a home in open source is working on all sorts of other aspects around open source projects.
What a great message to end on.
Thank you, Michael.
Thanks so much for your time, Jonathan, and for everything you do in the community.
Oh, likewise. Thank you for having me on your wonderful podcast.
Oh, cheers. Take care.
Take care. Goodbye.